ACM student chapter. After a short break and a great talk in the morning, we are ready to be on a thrilling ride again. Now, moving ahead, we have Professor Meena Mahajan, who is who is a professor at the Institute of Mathematical Sciences (CIT) and member of Program Committee SAT 2021 and a member Executive Council of the Indian Association for Research in Computer Science (IARCS). Other than that, she is also an ACM eminent speaker. Without wasting any more time, I would like to call Professor Meena Mahajan for her talk on Compute, 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 how hard it can get.
Thank you very much, Harsh, for the introduction, and thank you also, Sir Rahul, for the invitation to speak at this event. Start share. So I hope my screen is visible now. Okay, so now that I have started sharing my screen, I cannot see the thumbnail videos or the chat nicely. Also. So before we get started, also because this is an ACM Foundation Day event, I thought maybe I should show briefly this slide about activities of ACM, and in particular ACM India. There are a whole lot of activities which can really be called IRIS, which is for students and educators. It is. Let me start with a what looks like a puzzle. This is a tiling puzzle. So you have these tiles which are in these two very weird shapes. Okay, normal tiles are not like this. Normal tiles which you have seen in your bathrooms or kitchens or floors, they're usually squares. Sometimes hexagons, but usually squares. But here are these weird shaped tiles, and using these we want to tile the entire plane. The question is it possible? Well, with this example, it's very easy to see it's possible. And here is one way. This is not the only way in which you can do it, but here is certainly one way in which we can cover up the entire plane. So, what do they mean by tiling the plane? Every point on the plane should have some tile on it, and on no point should there be two tiles. No, that's absolutely not allowed. So, it should cover everything without gaps and without overlaps. So, here is one way in which we can do this with these two shapes. Now I change the shapes and I say, okay, you have tiles like this. Is it still possible to tile the plane? Well, yes, it is possible to tile the plane. Here is one way in which you can do it. Again, this may not be the only way. Now I give you these shapes, and a little bit of thought should convince you that actually with this it's not possible to tile the plane because there is a little gap inside that red tile which the blue tile cannot quite reach. And assuming that you cannot turn around the tiles or rotate them, there will always be gaps. So if this is the shape, if these are the shapes given, then it is not possible to tile the plane. So these three examples that we saw, they are like a little bit like jigsaw puzzles. Piece things together so that you form a nice picture. That's what we do in a jigsaw puzzle. Here we're saying piece things together and just provide a uniform surface. Now I give you a more complicated tile. Okay, say now with this can you tile the plane? So at this point, the person who's trying to address this question probably, like some of you also may have this opinion that this is getting to be a bit tedious. After all, for how many times are you going to break your head trying to figure out, can I do this, can I not do this? Maybe for this one, you may want to think a little bit, is it really possible to do it or not? But anyway, this stick figure, this cartoon figure here has given up. Okay, this fellow says, I don't want to sit and look at one tile or two tiles at a time and say, can I do this? But we are in the modern age of computers. So why don't I just write a program? And then I have to think to write a program. But once the program is written, you can give me any tiles and I don't have to think anymore. The program will give me the answer. Right? So this is a coding enthusiast, clearly, which I'm sure that many of you also are. Coding is a very nice and exciting enterprise to do when you're a computer science and information technology student. So this person decides to write a program which will take as input a description of the shapes of the tiles and produce as output an answer. Yes, it's possible to tile the plane. This is how we will do it. Or no, it is not possible. Okay. So this fellow gets to work, writes the program, debugs it, gets it running, gives it this tile as input, and produces this output with a clear indication of how to extend this in all directions. So, okay, so this tile, it's possible to tile the plane. Now I throw a even more weird, complicated looking tile at the person, but the person is completely unfazed because the program is already written, right? So you just take the tile, the description of this new tile, give it as input to this program, out comes the answer. It is possible to extend it in all directions. Then I give this bunch of tiles. There's some already in this. I've shown 4 tiles, but there are some more inside. So I'm giving now a bunch of some 10, 12 tiles, which are very weird shapes. Look at this long arm here. Look at some gaps here. And a description of the tiles can be created, given as input to the program, which is what our programmer friend does, gives the tiles as input to the program. And then it's waiting and waiting and waiting, and the program is not given an answer. It's like 10 minutes, 20 minutes, half an hour, 1 hour. When did you last wait for 1 hour for a program to finish? You probably don't remember such a time, right? So this is the point at which this person starts getting a bit worried. And when a friend walks in, the programmer says, what's wrong with my program? Is it ever going to halt? Maybe this is just a bug in the program. I'm waiting here like a fool. So the question he's asking is my program ever going to halt? And the friend just picks up that line and says, wait, I'll write a program to check that. I don't want to see whether your code is correct, whether it is really solving tiling or no, because I'm not interested in tiling. But this is a meta question, right? Here is a program. Does it halt at all on this particular input? So this fellow is going to write a program to check that. He gets to work. He writes a program. The input to this program is the code for another program, right? So he writes this program, gives this person's program as input, right? And then the same thing happens. Second stick figure, his program does not seem to stop. At least not for 10 minutes, half an hour, 1 hour. 1 hour, the program has not yet stopped. So, the first person is a bit gleeful. Haha, your program also hung. But actually, they are not sure that the program has hung. It's been 1 hour since the program is running. It has not yet halted. Maybe if we just give it 5 more minutes, it may halt. So how do you decide when you should stop waiting? You're sure now that the program is not going to halt. It has gone into an infinite loop and you should cut it short. How will you even decide this? Along comes a third person. Says, okay, it's not your fault. Don't be too hard on yourselves. It's not your fault. Even I can't write such a program which decides whether a program will always halt. Even I can't write. Now, this sounds so arrogant. Huh? Like I'm so smart and I can't write it, so you can't. Well, but it's not that she's saying. She's saying it's not because I'm not smart enough that I can't write such a program. It's because nobody in the world can write such a program. Now, this is a very tall claim. This person is saying it's not just that you or me, none of us can write a program. They're saying that such a program simply does not exist. And such a program does not exist. This is what is called an undecidable problem. This is what we want. We want a program which does the task of this gray diamond here. So what is this task it is supposed to do? The program should take as input a code C, the code of another program, data D, the data which is to be given to that program. So basically it takes as input 2 files. This bigger program takes as input 2 files. One of those files is supposed to contain another program. One of those files is supposed to contain data. And then this program will either say, no, C when run on D does not halt. Or it will say, yes, C when run on D does halt. Either way, this new program halts. So it is not an option for the new program to simply run C on D. See? Because if it just runs C on D and C does not halt, then this new program also won't halt. So it should figure out whether C halts on D without actually running C on D by doing something else. So it has to analyze the program in some way. And what we are claiming is that such a program with this behavior does not exist. How can we prove such a thing? So this fact that such a program does not exist was proved by Alan Turing in the days when there were no computers. When there were calculators, there were some big clunky mechanical devices, but the way we understand computers today, digital computers had not yet been built. But nonetheless, this theorem was already in 1936. Turing proved that whenever computers come around, it will be impossible to answer this question for those computers. It's a very powerful kind of statement to make. So the fact that this problem does not have a program which solves it, in the lingo that we use in computability theory, we say that this problem is not computable, it's uncomputable, or it is undecidable. So an algorithm decides. It gives a yes or no answer for a problem. And this problem, the halting problem, does a program halt on a data, is an undecidable problem. Now the halting problem, remember, was the problem which the second figure was trying to address. The first figure was not trying to address halting. The first fellow was just trying to solve tiling. It turns out that the tiling problem is also undecidable. So it's not just that the second fellow made the task harder. Even the first person's task given a program which tries to figure out whether some tiles can tile the plane, such a program, whether it halts or no, cannot be decided. It's an undecidable problem. Or the tiling problem being undecidable also simply means that there is no program which can take as input a shape of tiles and always give the correct answer. Yes, these tiles can tile the plane, or no, these tiles cannot tile the plane. Such a algorithm cannot be written. Such a program cannot be written. So if you have already seen this kind of thing before, then there's nothing much new. But if you haven't, then at this point you might be quite perplexed about how could you even prove such a statement. It's very different from saying, okay, I give you a program and you prove to me that this program is wrong. You can prove this program is wrong by actually giving an input code and data for which you know the correct answer. You run it through the program and show that the program is giving a wrong answer. So that you can do for a specific program. But here I'm not even giving you a program. I'm saying that no program that has already been written is solving this problem. No program that is yet to be written in the future also can correctly solve this problem. How can you even prove such a statement? At a philosophical level, it seems like an impossible task. But it's not impossible. So let me show you a one slide sketch of how one would prove that something is undecided. Like I said, if you have already seen this before, then this is just revision. But this is not something that is very commonly encountered, these kind of arguments. So let's go through it. Suppose the halting problem were not undecidable. Suppose it were decidable. So what does that mean? That means that there is some program, and that is this program which I have drawn here in a green box. There is a program P which can take as input a file containing a program C, another file containing data D, and it can give the one of these two answers. Either it will say yes, C halts on D, or it will say no, C does not halt on D. Does not halt meaning it goes into an infinite loop. So suppose there is a program like this. No matter what C or D is given, C D is given, it gives one of these two answers, and its answer is always correct. What I'm going to do is I want to show that such a program cannot exist, right? So to show that such a program cannot exist, I must cook up some input on which this program will be wrong. And to cook up that input, let me write another program which uses P. So the other program which I'm going to write, it's like this. So this is a new program Q which I'm going to use to track P. Q takes as input only one file, unlike P which takes two files, C and D. Q takes only one file. And it does not even give a yes or no answer. Q is expected to, on some inputs it will halt, and on some inputs it will not halt. Obviously, I don't want Q to be a program which always halts, because then you feed it to P and P can just say yes, it halts, and P will be fine. So Q will be a program which sometimes halts, sometimes does not halt. What does Q do? It takes A, makes another copy of it. So now you have two files. Okay? Both those files, they contain the contents are the same. But what are the contents? It's some binary string, right? And that binary string is entirely up to you. You can interpret it as a program. So interpreted as a program, maybe it is C. Interpreted as data, it is D. The same binary string I can interpret as program and data. This was one of Turing's great insights, that the indistinguishability between program and data. So what this program Q does is it copies A into itself, so as itself. So it has now these two files. It gives these two files to P. So it's calling P as a subroutine. Okay? Q is a program which calls P as a subroutine. Now what will P do? P is going to have one of these two outputs, right? So either it will say on this side C halts on D, meaning A halts on A, or it will say C loops on D, that is A loops on D. The program Q is slightly different. So it calls P as a subroutine. If P says A halts on A, then Q goes into a loop, an infinite loop from which it will never escape. But if P says that A loops on A, then Q immediately halts. Okay, this is my new program Q. Now notice that to write Q, I don't need to know whether P is correct or wrong. You give me any P claiming that it has this behavior, I can use P to write Q. Okay? I just make a subroutine call to P, and on the outputs of P, I attach instructions for an infinite loop or a halt. So if there is such a P, there is such a Q also. Okay. Now what do we do? Assuming there is such a P, there is this program Q, and I look at what happens when Q is given as input in the file A a description of Q. When will Q halt on Q? So suppose I give as input here this A, which I can initialize with anything. I give it the file which contains Q. And suppose Q halts. That means this thing came out here. That means P came out on this side, right? So that means P said that Q loops on Q. So Q halts on Q. If Q halts on Q, then it means that P said that Q loops on Q, which means that P made a mistake about Q. Q halted on Q, but P is saying that Q loops. So if we assume that P is not making a mistake, then Q cannot halt on Q. Q must go on this side. So Q must loop on Q. And what does that mean about P? It means that P said Q halts on Q. So if Q halts on Q, then P is saying, oh, Q looped. And if Q loops, then P is saying Q halted. Either way, the answer that P gives when its input is Q, comma Q is wrong. This is the contradiction. So if you're not completely convinced, you can give yourself a minute to just look at this some more and digest it. All we are saying is, if there is a program which claims to solve the halting problem, I can produce an input to this program, and the input to this program, the CD is going to be Q, comma Q, on which probably this program is wrong. This program cannot always be correct. On the program Q with input data Q, it must be wrong. This is a very nice argument. These are the types of arguments which are called diagonalization arguments. In spirit, although this does not look like that, for those amongst you who are sufficiently mathematically oriented, you may see that there is a certain similarity. It is essentially the same argument which tells you that there are real numbers which are not rationals. That's also a diagonalization argument. This is also a diagonalization argument. Okay, so this tells us that there is a very natural computational problem which in principle many of us would be interested in. You have a program and it seems to be running for a long time, and you would like to know, is it running, is it going to stop soon, or is it actually gone into a loop? It's a problem which is worth solving. It could add value to us, but we are saying that it is not possible to solve it. So then we could also ask, how undecidable is it? Is it that almost all inputs a program cannot decide, or is it just that there are a few isolated cases? Like here, there is this particular program Q on which P makes an error, but suppose on all other programs P is correct, that may be good enough, right? We just remember that we should avoid using that program on these inputs. So, in some vague sense, it makes sense to ask how undecidable. It turns out that this is very undecidable. Okay, there is no such thing as undecidable in just a small place. If the problem is undecidable, it may be right infinitely often, but it must also be wrong infinitely often. It cannot be that it is wrong only at a finite number of places. So any program which claims to solve the halting problem or which claims to solve the tiling problem, infinitely often, for infinitely many inputs, it is getting the answer. So that's not good news at all. So we should not be trying to solve the halting problem in this way. We should just try to write better code which will halt, which we can analyze explicitly and say why it works. Okay, at this point one may say, okay, who cares about this problem? You came to this halting problem because you wanted to see a tiling problem. I don't care about tiling the whole plane. It's a very artificial problem. In practice, you always have a finite area. One bathroom in your house has to be tiled. One airport terminal floor has to be tiled. There's some, the auditorium has to be tiled. It's finite. It may be large, but it is never infinite. I have a finite rectangle and I want to cover it. And maybe this problem is no longer undecidable. Just going from infinite to finite can completely change the nature of the problem. The other thing which you may say is this problem is so artificial because I had all these weird shapes for tiles. Whoever has weird shapes like that, you always have nice squares or hexagons. And in fact, typically the tiling problem that we encounter is one of color matching. You have tiles, which tiles go next to each other. You want to assemble the tiles in such a way as to make a nice pattern. So the right edge of this and the left edge of this should be perfectly aligned. They should create a nice pattern. So in fact, it turns out that these two settings are equivalent. So let's go into this setting. Here is a square of side 3. So 3 by 3 square with 9 squares. And these are the 9 tiles that I have. Each tile has a different set of colors. Okay? And I want to put them together into this area in such a way that adjacent edges get the same color. So let's just try. So I mean, is it possible or is it not possible? So let me try by start off by putting this tile here. Now the moment I put this tile here, in this position I can only put a tile which has this dirty gold on the left, right? And there is this tile. So let's put that. And now here I can only put a tile which has this dirty gold color on the bottom. There are two such tiles, this and this. So let's try with one of these. But now we are stuck because in this place I have to put a tile which has yellow on the left and yellow at the bottom, and you can see that there is no such tile. So this was a wrong choice. So we undo that and we put the other tile which could potentially have fitted there. And now I need something which is purple on the left, yellow on the right, which is this. And then I need here something which is golden at the bottom. There's only one more thing. I need something which is yellow on the left, and now you get the idea, right? One by one, I have picked up tiles from here, moved them there, and when I arrange them like this, you can see that all the boundaries respect the colors, right? So respecting the color is saying that yes, this tile fits next to this. Okay? This tile fits next to next because the colors on the edges which touch each other are the same. So this is a more practical problem in the sense that the set of tiles is given. They are all of a nice shape. They have colors constraints on the edges, and there is a finite area that we want to tile. Our friend says even if this is a seemingly simpler problem, I'm still going to write a program for it. I don't like solving these puzzles. Okay? So I don't want to figure out what tile goes where. I'll just write a program. To this program, I give as input these things, and then the program says, okay, it's possible to do it. Here's an answer. To the same program, I give as input this much of tiles. The program says it's not possible. Okay? And you can verify that, in fact, it is not possible. So now the question is this problem also undecidable? It turns out that this problem is not undecidable. There is such a program which always holds, which is always correct. Okay? What has changed from the previous setting? You may think that the main thing which has changed is the tile shapes are nice. No, that's not what has changed. What has changed is that we have gone from the infinite to the finite. And that makes a huge difference. So there is a program which always holds, which always correct. Question is, does that mean that the problem is solved? So this is now where real world computation comes in. The problem is not yet solved in the following sense. We may want to know how fast can it get the answer. So if the program which this fellow has written is a very simplistic program, it may just say, okay, let me try all possible placements of the tiles. 9 tiles, first tile, any of the 9 tiles can go. So I put it there. Then for the second place, there are 8 options. Third place, there are 7 options. So 9 factorial. And so on. So just try out all the possibilities. For each possibility, place the tiles that way and check whether all the constraints match. And keep doing this until you find something which matches, or you have finished all the possibilities. So this way you will always get an answer. That's what I meant when I said that there is such a program. It will always hold because the number of placements is finite. And the program will always be correct because it's trying out every possible placement. It will not miss out something. The catch is that the number of placements is huge. The 3x3, with a 2x2 grid and 3 types of tiles, there are more than 10 possibilities. 3x3 grid, there are more than 1500. You see how it grows. 4x4 grid, 16 factorial it looks like. Huh? But it's like maybe not quite 16 factorial because maybe there are only 3 types of tiles. Then it's like 3 raised to 16. Even 3 raised to 16 is a huge number. It's more than 2 million. If I restrict myself to just 2 colors, there are these 16 types of tiles. And depending on what constraints I have, you're going to get, with a 5x5 grid, you would get something like 10 raised to 17 possibilities. 6x6 grid, a million years in the fastest supercomputer in the world. In what sense can you say that this problem is solved? If you have a program to which you give the input and then it gives you the answer after a million years, for all practical purposes, it is not solved. So therefore, what this tells us is that we cannot write a simple program. We have to do something clever. And until we find that cleverer way of solving this problem, we cannot say that the problem is solved. Okay. So what do we do? Do we design a cleverer program or do we wait for a faster computer? So this waiting for a faster computer is not going to work. Okay? I mean, maybe 1 million years will come down to 500,000. A computer which is twice as fast, 10 times as fast, it will come to 0.1 million. 0.1 million years also. Can we really wait for the 1 lakh years? We really can't. So the main problem is that there is a combinatorial explosion. There are just too many possibilities. Checking all of them simply won't work. Maybe if you have a faster computer, it will work for 6 by 6. It will not work for 7 by 7. You have to make some progress, and basically you need to use cleverness, which is good for us because we are human programmers and we want to use for our talents, right? Okay, so we need the cleverer programs, so we need the clever programmers, which we are all in training for. Our only hope for an efficient program is to rule out lots of possibilities at one shot. At one shot, we should be able to say that, okay, all these possibilities of extending the tiling are not going to work, and we need to do something. Okay. What are the problems that we can solve efficiently? We can add numbers efficiently. I mean, adding numbers efficiently, not just as human beings, we have calculators, that abacuses, and so on for years, which do this very efficiently. So, this number which I have written here has so many digits, but I could give you a number which has maybe 1 million digits. The digits of the number are written in a file. So I give you two files which have a million digits each, and I want you to add the numbers in these two files. You can write a program which will do this addition very fast. So this is, in that sense, this is a problem which can be solved efficiently. Multiplication. Again, here, for purposes of showing on the slide, I have written small numbers, but even huge, multiplying huge numbers. We can write programs, we can construct circuits which will do this very fast. Sorting numbers. There is a list of numbers. They may be numbers, they may be words, strings, whatever. But you want them finally in sorted order. And this is a task which is required all the time in practical applications when you have dictionaries, directories, and so on. You need data in a sorted format. And yes, we know how to do it. Finding your way through a maze. This is a bulbulaya. Finding you enter here, you want to exit here without getting caught in some kind of a loop. Well, if the input to the maze is given to the program in some form, finding a route out, this is something that the program can find efficiently. These are relatively simple examples. Here are some more non-trivial examples which also, it turns out, we know how to find efficiently. Suppose you want to find teams of two. So you have, imagine a classroom with two sections. So there are children from one section, they are labeled blue, children from another section labeled pink, and then you want to form teams of two for some event. That each team should have one from this section and one from this section. But there are some lines joining them. These lines are friendships. So you cannot put these two fellows into the same team if they are not friends with each other. They will just fight and bring down the whole thing. So there is, well, maybe not friendship, maybe compatibility, that they can work together. So these edges represent compatibility, and the colors represent who can go into the same team. So blue and blue cannot be one team, pink and pink cannot be one team. Okay? And now you want to form teams. So form teams of two, each team one red, one blue, teammates must be compatible. Well, here's one way of doing it. Here are some teams that I have formed. They are all compatible. But this is not a good way. For instance, this person is not in any team. This person is not in any team. If I want to put this person in a team, both the persons whom he is compatible with are in some other team. There's nobody free. So this is not a good way of teaming them up. But here's another way of teaming up. Again, everything matches the compatibility, and now everybody is paired up. Every kid is in a team. So this is what we are looking for. So the input is a structure like this. Persons, call them nodes in a graph. You have these nodes in a graph. The nodes are colored, two different types, and there are these edges. So if you may recall from your data structures and graphs course, then these are what are called bipartite graphs. And in this bipartite graph, we are trying to find the perfect matching, a matching which pairs up the nodes perfectly. This is something which it's not very easy. If you have not thought about it deeply enough, you cannot immediately come up with an algorithm which will solve this efficiently. You can come up with an algorithm which will solve this brute force, try all possible pairings. But to come up with something which is fast requires work. But this work was done many years ago. In 1966, this problem was solved. An efficient algorithm for this problem was devised. Here's another problem which I'm sure you would have seen in some form or the other. There is a graph like this. These nodes are, maybe think of them as cities or locations within a city. And these are the connecting roads or within a city or across cities, flight routes. The numbers are the cost of the flight or the time to travel by road. And now I ask you You want to go from A to E. What is the cheapest way of going? Oh, there's a direct connection, but it costs 9. There's a less direct connection via C, but it costs 8. That's better than 9. But there's another connection, B, C, E, and that costs only 7. Is there anything which is even cheaper? Well, there isn't. This is the cheapest. So this is the kind of question that could crop up in many practical settings, and we have efficient algorithms which can solve this. Cheapest A to G route is here. Cheap. So these are examples for this is an example of the problem for which we do know how to solve. Now here's a different kind of problem. This is the tiling problem which I described some time ago, for which I did not at that point say whether there is an efficient problem or no. I just said program or no. I just said that the brute force method is not efficient. It turns out that as of now, we do not know whether there is an efficient program for this. But it's not undecidable. There is a program, and maybe there also is an efficient program. There is no proof that there is no efficient program. Maybe there is one, we just don't know. On the other hand, checking a tiling, as opposed to finding a tiling, if I give you a tiling and I ask you check whether this is okay, that can be done efficiently. You have to go over all the edges and check that all the constraints are met. So in some sense, this is a phenomenon which happens in many problems. Finding a solution is hard. Checking a solution is easy. And I think the students here may particularly appreciate the setting that as a teacher to set an assignment question and to correct an assignment solution that has been turned in is an easier task than for the student to actually solve the assignment. As a teacher, I may not know the answer to the solution, but if you give me a LH solution, I can check it. I'm not saying that the teacher's job is easier because you have to set an assignment which also gives value to assessment. But once the assignment has been set, finding a solution is harder than checking the solution. So we may want to investigate this. What are the problems for which solutions can be verified efficiently? Maybe we don't know whether we can find them, but we can verify them efficiently. So here's a very bizarre looking problem. A set of numbers is a huge set of very large numbers, and you want to split these numbers into two groups. The numbers in each group, when you add up, the total is the same. You may ask, why would anybody want to solve such a problem? Is it a practical problem at all? It's a very practical problem, not just in computer science. It's a very real world practical problem. As an aside thing, imagine that these numbers are the values of some shares that a person owns, and the person wills this to his or her two children, saying divide it equally. They can liquidate all the shares and then divide the cash, but if they want to keep the shares, they have to split them in some nice way. Or this is the value of some gold jewelry that a family owns, and it has to be divided without breaking the jewelry because these are heirlooms. What goes to whom? The values on both sides should add up to the same amount. That's a practical problem. Okay? But looking at these numbers is not going to be easy to figure out how to split them. And depending on how many numbers there are, how many splits are there? If you have n numbers, there are 2 raised to n minus 1 ways of splitting them into these two sets. So you can't go through all of them. 2 raised to n minus 1 is too large a number. But if I give you a split like this, you can easily add up. We already said addition is efficiently doable. So you can just add up these numbers in your calculator and check that the sums on both sides are the same. So checking a solution is very easy. Finding a solution, we don't know how to do it quickly. We can find solutions, but quickly we don't know how to. Here's another example taking off from the previous thing. Instead of teams of 2, now I want teams of 3. So there are 3 sections and there are compatibility relations. These 3 are compatible. These 3 are compatible, but there is nothing connecting these 3. So these 3 are not compatible. So you have some compatibility relations. Form teams of 3. And here is one way in which you can do it. Everybody is covered. Teams of 2, I said we know how to find solutions. Teams of 3, we don't know how to find solutions as of now. But if somebody gives a solution, we can check that it is a valid solution. Cheap tours. How is this different from what we saw earlier? So what we saw earlier was cheap routes. I give you one A and one E and I say go from E to E. Here, what am I doing in cheap tours? I want to start at A and I want to go to E But I just don't want to go from A to E. I want to go from A to E touching all nodes. Go via all the nodes. And then I have an overall budget. Is it possible to go from A to E touching all the nodes with a budget of 23? Here's a way of doing it. Is this a practical problem? In fact, this problem is what is called the traveling salesman problem. A salesman who has to travel from client to client trying to sell whatever product his company makes. And he has a travel budget. There's only so much you can spend on auto fare or petrol fare or whatever. So there is a budget and you have to hit all these clients. Is it even possible to do this? So there are lots of these kinds of problems where checking the solution seems easier than finding a solution. Tiling, Sudoku. So Sudoku puzzles, if some of you are addicted to them, then you would know that checking is completely trivial, but solving requires work. Crosswords. In the same way, checking the proof of a mathematical theorem. Checking the proof is easier than coming up with the proof in the first place. Same applies to engineering tasks also. Designing this kind of thing, designing a new aircraft, designing an automobile. Somebody comes up with a design, it is easier to check whether that design is okay. To come up with the design in the first place is hard. In fact, even something far removed from science and engineering, music. This, I think, everybody here should be able to appreciate that composing music or even rendering, performing music is a much harder task than appreciating. If the music is produced in front of you, you can say, yes, this is good music, no, this is not good music. Well, not all of us can, but many more of us can, then can actually go and perform. Right? So it's the same phenomenon which is happening here. Checking or appreciating versus finding or creating. So creating requires creativity. Appreciating requires an awareness, but it does not necessarily require the same level of creativity. Okay, so let's get back to more concrete problems. Finding versus checking. So we have a bunch of problems which seem to be possible to solve fast in the sense of finding solutions fast. Addition, multiplication, sorting, cheap routes, and so on. Then we have a bunch of problems for which we don't know how to find the solutions as of now, but claimed solutions can be checked efficiently. There are also problems for which even checking a solution is very hard. And here I've put in this word Antakshari. I mean, maybe you do not even think of Antakshari as a computational problem, but there is a setting in which it is very computational. If I give you a book of songs, I say that your Antakshari is limited to only using songs from this book. So it's like saying that the dictionary is fixed. Well, it's not fixed. It may change. Tomorrow I may give you a different song. So the input is now a dictionary of songs. And the question that we are asking, the computational problem is, if this is the dictionary, does the team which starts first, can that team always win? Who has a winning strategy? Okay. So this is also a very hard problem computationally. But even if a winning strategy is given, checking whether that is really a winning strategy is hard. So we are not going to talk about this problem. Let's just limit ourselves to these. Either it should be possible to find a solution quickly, or if not, at least checking a given solution quickly should be possible. Okay? One of these two. And these are the terms quickly needs to be quantified. What do we mean by quick? So the way we normally quantify this is our definition of efficient program in theoretical computer science is polynomial time. The number of steps required should be polynomial in the input data cells. So the input is of size n. Then the number of steps of the program should be some polynomial in n, 1000 n, 100 n cubed, 5 n raised to 10, 5 n raised to 7, 7 n raised to 18, or something like that. N raised to a constant, not 2 raised to n, not 5 raised to n. Okay? So this is an exponential growth. Now this exponential is a number which we have been hearing a lot in the context of COVID. But by exponential, basically we mean that this n has gone up in the exponent. Right? So we want the growth in terms of the input size to be a polynomial function and not a super polynomial function. Exponential is one particular super polynomial, but we don't want any super polynomial. And the reason why we want polynomial growth as opposed to something which is super polynomial is that any super polynomial function, here I've plotted input size here and the time here for different functions. Super polynomial quickly overtakes any polynomial. The polynomial may have very high degree, it might be n raised to 1000. But even if it is n raised to 1000, 2 raised to n will overtake it. It may need a little longer to overtake. So instead of at 5 by 5, it may overtake it at 10 by 10 or 15 by 15. But pretty soon it will overtake. So to give you a feel for numbers, 100 n cube is 11 zeros after 1. 2 raised at 1000, at n equals 1000. And n equals 1000 is a fairly small input in today's world. No? Today's world, Google algorithms, which do Google search, are dealing with millions of records. 1000 is like nothing. So even at 1000, this 100 n cube is like 10 raised to 11. But 2 raised to n is 300 zeros after 1. Is that even a feasible time? The total number of hydrogen atoms in the entire universe is only 10 raised to 80. And what are we talking about 10 raised to 300? A program which has a runtime like 2 raised to n on an input of size 1000, when is it going to stop? There is a very nice video put out recently by the Simons Institute for the Theory of Computing. This is at the University of California in Berkeley, where they are trying to explain this polynomial versus exponential growth. And the term they use for this is until the sun engulfs the earth. So it's like saying that these kind of answers will not come in your lifetime, in my lifetime. They will not come in the lifetime of the earth. So it's way beyond infeasible. There is no hope of usefully using such an algorithm. So this is what we mean by efficient, that it should run in polynomial time. And these problems here, which I said we can find solutions fast, they are the class of problems with polynomial time solutions. These are the class of problems for which, so this class we call NP as opposed to P. NP stands for, it does not stand for not polynomial. It stands for non-deterministic polynomial. What does that non-deterministic polynomial mean? So the non-deterministic refers to the fact that non-determinism is like guessing, not guesswork. So you can guess a solution, maybe. But after you have guessed it, you have to check whether it is correct or not. And that checking can be done in polynomial time. So this class NP, non-deterministic polynomial time, consists of problems for which a guess and verify model works. The guessing will be done by somebody, presumably a human being and not a program, somebody with creativity to think up the solution. And once the solution comes, verifying that solution can be done by a computer. You should think of the computer as a dumb program, right? It may be written by a very clever programmer, but after all that, it just does what it has to do. So these are the classes P versus NP. And the big question in theoretical computer science is whether P is equal to NP or whether P is not equal to NP. What does it mean P equal to NP? Well, P is a class of problems, NP is a class of problems. Every problem in P is inside NP. This Venn diagram you can see, P is contained in. The question is it a proper subset or is it an equality? And this question, depending on whom you ask, but there is pretty much unanimity in the theoretical computer science world, it is the central unsolved problem of theoretical computer science. It's the most important challenge in theoretical computer science. There are people who say it's the most important challenge in computer science, in mathematical science. Some claims get more bombastic. There are people, computer scientists, who have said it's one of the deepest questions the human beings have ever asked. We need not agree with all these comments. Okay? Here's a comment which says that, oh, of course P and NP are different, just that we don't know how to prove it. This is obviously coming from somebody who believes that creative spark is something which is necessary. Creativity is required to find a solution. So this question, a formal resolution of this question, is P equal to NP or is P not equal to NP, is a $1 million prize-winning problem, a millennium problem of the Clay Math Institute. So the fact that it is a problem listed there in 2000, the year 2000, this Clay Math Institute listed out some problems which they felt are the important problems at the turn of the century. Right? And this is a problem which comes squarely from computer science. It is not, in that sense, a pure math problem. Increasingly, mathematicians are turning their attention to this problem, but it is a computational problem. We should never lose sight of this. So it is, in some sense, a contribution of computer science to mathematics. And attempts to solve this problem have thrown up a lot of very interesting mathematics. Why is this question so significant? Well, if P is equal to NP, then what it means is that whenever a problem is in NP, that is, whenever we can verify a solution quickly, then that same problem is also in P, so we can also find a solution quickly. And the implications of that, if P were turned out to be equal to NP, overnight there would be huge strides in all kinds of medical research. Medical research very often is trying to find solutions. What is the best way of folding or threading a protein? What is the best fit DNA sequence? Here I have mentioned cancer cure research, but maybe in the current climate I should have said vaccine development research also. No, there's a lot of very non-trivial biology that goes into this, but there is also a lot of computation. It's a hard computational task finding the right thing eventually. And if P is equal to NP, we could be able to do these searches so much faster. So with improvements in medical science, quality of life will improve, right? There would be, well, perfect maybe again another bombastic claim, but far better maybe than today. Artificial intelligence software will come about. This I'm not so sure is a plus point. Huh? Maybe mathematicians will become redundant. We may get replaced by efficient theorem discovering programs. After all, if you can check a proof, then you can also find a proof. Well, jokes apart, on the flip side, if P is equal to NP, our digital world is it's going to come crashing down. There's not going to be any digital privacy. No passwords are going to be safe. If you can check whether a password matches correctly, then you will also be able to find that password efficiently. Every encryption scheme that is currently in use for all kinds of authentications, banking transactions, e-commerce transactions, whatever, digital signatures, they are all based on premises that NP and P are distinct. And if NP and P are the same, then that safety goes for a toss. You will not be able to do your digital transactions. So it's not a good world having P equals NP. Here's a quote from Scott Aronson, who is a CS professor currently at Texas. At the time when he made this quote, he was at MIT. He said, if P is equal to NP, then the world would be a very different place from what we assume it to be. There would be no special value to creative leaps. There would be no fundamental gap between solving a problem and recognizing the solution. Anyone who can appreciate a symphony will be Mozart. Anybody who can follow a step-by-step argument will be Gauss. Anybody who can recognize a good investment strategy would be Warren Buffett. This is to say that it's not a good world. What if P is not equal to NP? Well, first, the good things. Our online transactions are safe, our online secrets are safe. The bad things, we can't find cheapest tours efficiently. Vacation is over before we even find the best way of figuring out how to use our money. So basically, if P is not equal to NP, then we have to settle for what is good enough. We can't aim for the best because it's going to take too long to find the best. And there was a very nice book written about this by Lance Fortno, and a review of it in the New Yorker said that to postulate that P is not equal to NP is to allow for a world of mystery. You don't know what is the best solution. There is a mystery about it. It's difficult finding the best solution. It is frustrating you're trying to find it and you're not able to find it. But more than the difficulty and the frustration, the first point is mystery. And mystery, there is something which is pleasing there. Because there is a challenge, there is the pleasure of discovery, of inquiry, and there isn't instant gratification, there is a pleasure of anticipation. So it's a very philosophical take. So here's this book that I mentioned by Lance Fortno. He is currently at Chicago. At the time when he wrote the book, he was at Georgia Tech, and this book he wrote, The Golden Ticket, PNP and the Search for the Impossible. And I would, if you have found this description of what are the difference between easy and hard problems and what effect it can have, then this is what I would like to recommend. Let me just spend actually, I don't know. Do I have 5 more minutes? Would that be okay?
Yes, ma'am, please.
Okay. So I just wanted to spend a little bit more time to describe, now that we have this setting where, so many interesting problems seem to be in NP, we don't know that they are NP, what can we do? I mean, we can't just give up and say, okay, it's an NP, so I can't solve it. They are real world problems. We need to do something with them. Can we even compare hard problems? So equal sharing, cheap tools, these are both problems which I had drawn in that set for NP. They were not in P. They both seem hard. But maybe they are not equally hard. Maybe neither of them is in P, but still it's possible that one is harder than the other. Do we have any theoretical tool to even tell us in what sense one problem is harder than the other? So it turns out, yes, there are ways to compare hard problems. For instance, here is one way I'm going to tell you between these two problems. Suppose I have a program for equal sharing. This program expects as input a bunch of numbers and then says, yes, you can split them into 2 sets with the same sum. No, you can't split them. Okay. I want to ask, is it possible to use this program as a subroutine to solve the cheap tools problem? What is the input to the cheap tools problem? There's a network, there's a start node and an end node, and there's a budget. If P were available magically as a subroutine, can I solve this problem? So now I want to write a program Q which calls P as a subroutine and solves cheap tools. So what would this have to do? This would have to somehow transform this input into a list of numbers. Because if you want to call P as a subroutine, you have to give it some numbers. Now, those numbers will obviously depend on the network. It will depend on the budget and all. But basically, this transform routine should take the network, the nodes, the budgets, and produce a string of numbers. And it should have certain properties. If T maps an instance here to a set of numbers for which the answer is, it should map a yes instance here. Yes, there is a cheap tour to a set of numbers for which there is equal sharing possible. And it should map a no instance here. No, there is no cheap tour to a set of numbers for which equal sharing is not possible. So if T maps yes cheap tours to yes equal sharing and no cheap tours to no equal sharing, then this program Q, which runs T on its input to produce this set and then just blindly calls P as a subroutine, this program Q would be correct for cheap tours. Right? All we need is to be able to do this transformation with this property. But if this transformation is also efficient, remember efficient means polynomial time. If it is also efficient, then whenever equal sharing can be solved efficiently, the whole box is efficient. So cheap tours can also be solved efficiently. So if I am able to come up with a transformation routine like this, which is correct and which is efficient, then that transformation routine tells me that whenever equal shares can be solved, cheap tours can also be solved. Okay? Cheap tours is not harder than equal shares. In other words, equal shares is at least as hard as cheap tours. So we are making a comparison between these two problems without actually solving either of those. It's not that I have solved cheap tours. It's not as if I've solved equal sharing. I have only given you a transformation routine, which is efficient. And to give that transformation routine, to conclude that cheap tours is not harder than equal shares, I just need an efficient transformation routine. I don't need the program for equal shares. I don't need to know that an efficient program for equal shares exists. So we do have a method of comparing problems in this abstract way, and that leads to this notion of NP completeness. There are many problems which are in NP, that is, we can verify solutions efficiently. We don't know which of them are really hard. We know some are not hard, but we don't know which are really hard. But we can still compare them. And there is this class of problems called NP complete problems, which are the hardest problems in NP. They are at least as hard as every other problem in NP. Cheap tours, equal sharing, teams of three, these are all NP complete problems. So cheap tours is also, like I said, it's called a traveling salesman problem. Teams of three is called three-dimensional matching. These are NP complete, which means that every other problem in NP can be transformed to one of them. Well, you think of teams of three, every other problem can be, even equal sharing can be transformed. So these three can also be transformed to each other. So if you think of in shopping, you have these, buy one get two, buy two get one free, buy three get one free. Here is the other way around. Solve one get 1,000 free. If you solve one NP complete problem efficiently, you would have got efficient programs for everything in NP. So that's one significance of NP completeness. How do you deal with NP completeness? Well, why is it useful to know that a problem is NP complete? There's a lovely slide in this book by Gary and Johnson. Gary and Johnson wrote a book in the 70s about the theory of NP completeness. When NP completeness was first established in the early 70s, and this book was some years after that. And they showed this programmer who is being hassled by his boss. He writes a program for some problem, and the boss says, I want a faster program, I want a faster program. Can't you do better than this? And finally, at some point, the programmer realizes that the problem at hand is an NP complete problem. He is just a mere programmer. He is not a great computer science researcher. How can he solve this breakthrough problem? But how can he convince his boss? So the cartoon shows him with a line of people behind him, like, I can't solve this problem, but neither can all of these famous people. So don't expect me. So it's useful to know that a problem is NP complete. Don't break your heads against it. But what do? You can't solve it. You still have to deal with it. So what you can do is to look for structure in your application. So there could be, for instance, three-dimensional matching. It's an NP complete problem. But maybe the three sets that you have from your application, they have some nicer structure. Maybe the underlying graph is planar or something like that. And when that happens, the NP completeness proof doesn't go through. suddenly the problem becomes easy. So try to exploit as much structure as is possible from the real application, and you may still be able to come up with an efficient algorithm. It's not solving the NP-complete problem in its full generality, but it is solving the instances which come up in your application, and that is what matters to you. The other thing you could do is to look for bounds on your inputs. For instance, this cheap tours problem is hard. The problem is hard, yes, but it is hard because your inputs could be varied. But for an actual traveling salesman, maybe there is a fixed budget. In one day you cannot spend more than 1,000 rupees on cab. Now you don't have to bother writing a program which can deal with 2,000 rupees, 3,000 rupees budget. It only has to work with up to 1,000 rupees. And with that cap, you can perhaps find efficient algorithms. Use those bounds. You could also look for good enough solutions. There are these approximation algorithms, which they are not finding the best solutions, not necessarily finding the best solutions, but they are giving you solutions which are close enough to the best. And it's very interesting. So they give you solutions which are close enough to the best without even knowing what is the best. For instance, this cheap tours traveling salesman problem. There is a very efficient algorithm which will produce a tour, and if the tour has some cost, the produced tour has cost P. P is a bad. It has some cost R. Then probably we can say that the best tour here is at least R by 2. So you are at most a factor of 2 away from the best. I don't know what is the exact value of the best. Maybe R itself is the best, but I am not too much beyond that. So such approximation algorithms can be designed also. So these are various ways in which you can cope. NP completeness problems, it is unfortunate or fortunate depending on your viewpoint that some problems are NP complete, but they are not going away. You still have to solve them for practical applications, and you have to use this extra information that may come up from those practical applications. So and there are other ways also to manage. Life just goes on, so you have to deal with it. Okay, so this is my last slide, just to summarize the big question which I am trying to emphasize. The big question in complexity theory, in theoretical computer science, is whether P is equal to NP or no. One setting says that checkable implies findable. The other setting says that essentially there is no shortcut to avoid an existing search. And what is the truth is perhaps something that we will never know. We don't know whether a solution will come up in your lifetime or my lifetime. So it may be one of those forever mysteries of the universe. Okay, so with that I end my talk. Thank you very much. I'm happy to take questions, or even if not specific questions, just comments is also absolutely fine.
Yeah, thank you so much, ma'am, for sparing out your time. We got a separate insight on the algorithms, on how you transform the daily life problems to the computational problems. So, ma'am, on YouTube, there are a few questions coming up in the live chat. So, one student is asking, he wants to pursue this domain of computational mathematics, how he should proceed towards it.
Oh, okay. So the problems which I described, they were of two different flavors. One was algorithm design, right? You're trying to come up with better and better algorithms for problems. But the PNP question comes from complexity theory, understanding the computational hardness of specific problems. So computational complexity is a subfield of theoretical computer science. If you want to pursue it as a research goal, then you have to get into a master's or a PhD program where there is theoretical computer science as the main area. Okay? So you would have to focus on the theory courses, theory of computing, discrete mathematics, algorithms, and design analysis of algorithms would also be important, because you cannot do complexity theory without knowing what the algorithms design is. But you would have, if you want to pursue computational complexity in itself as a goal, you need to be in a theoretical computer science program. That is one way to pursue it. The other way to pursue it is that you want to be up to date with results of significance from complexity theory as they affect your application domain. And this is something which cannot be underestimated enough. Unfortunately, it is not valued enough. I would say that it doesn't matter whether you are a theoretical or a non-theoretical computer scientist. Every computer scientist would be able to get something out of appreciating what is happening in complexity theory. And for that, I would say it may not be necessary to do a systematic study program in theoretical computer science. You would need to follow popular talks on these topics. And one of the things which I mentioned along the way was the Simons Institute of the Theory of Computing, which puts out such videos every now and then. There are other places also. So just following those, keeping abreast of what are the kind of challenges and what are the kind of closures that have been obtained would also be a very interesting way to keep abreast of things.
Yeah, thank you, ma'am. I hope that answers the question.
I hope
So,
so.
next question is like nowadays machine learning is on boom. So, what do you think? Like the NP problems can be solved in that AI or ML way, or is it still unsolvable by them as well?
So I think that the domains are somewhat different, but so AI ML actually there are a couple of other talks I know which also emphasize a lot that there is a distinction between AI and ML. ML is but a small part of AI, right? So in AI, every success that we have met with, every time there has been success, somebody proudly announces AI is reaching its goal, and then the goalpost has shifted. You do something well, and then, oh, this is not good enough, you need to do this. Then more innovative algorithms come up which reach that, and then this is not good enough, you need to do something. So ML is probably easier understandable because the goals are more concretely well defined. With ML, are we able to solve these problems? I would say the answer still remains no as of now. In particular, a lot of ML, a lot of deep learning based algorithms do talk about learning using neural nets of various kinds. And one of the theoretical models of neural nets is what are called threshold circuits. And it is a very sad commentary on where we have reached with computational complexity, that currently we do not even have provable lower bounds for results which say categorically that such and such a function cannot be computed by a threshold circuit of polynomial size and depth 2. Depth 2 means a neural network with one hidden layer. Okay? Forget about typical deep learning things which are talking about 4 or 5 layers now. One hidden layer. Admittedly, these threshold circuits are not full-fledged neural networks. They are not really using ReLU. They're just using basic linear threshold functions. But even with these, we do not know what can be done and what cannot be done. We do not have a good enough understanding of this. So, in terms of there is a difference between the end goals itself. So in ML or in the larger setting of AI, you are trying to prove upper bounds that some tasks can be done. Computational complexity is trying to say that some tasks cannot be done within these resource bounds. So obviously, the cannot be done part is harder to establish because it's against all. It's like the undecidability thing that we looked at. But we really don't know. So even these small threshold circuits, we do not understand those bounds well enough. We do not understand their limitations and also their capabilities. So whether they are going to be capable enough to solve all NP-complete problems is something which is completely up in the air as of now. It is possible that they can do it, but I would not say that we are anywhere near showing that it is indeed possible.
Okay, ma'am. That's really great. So, thank you so much for sparing out your time, and I would like to extend a special thanks from the whole USICT team. Just a small request to everyone: if everyone can switch on their cameras so that we can have a group photograph to
That's nice.
frame this. Yeah. Harsh, can you please stop screen sharing so that we can click a photo? Yeah. So thank you everyone for joining in, and thank you, ma'am, for taking out your time. And we look forward to having you again on such beautiful topics.
Yeah, thank you very much. I really enjoyed being here, and I hope that you did. All of you did get something of value out of this, because this is kind of an offbeat. This is not something that is taught in a typical college course, but I hope that you did enjoy it. I'd be happy to be in touch with you in the future also, and you can send me email if you have any specific questions or comments. Thank you very much.
Thank you everyone for joining in. With this, we come to an end of the celebration of 75th ACM Foundation Day. So as the motto of ACM says, like we have to promote computing as science and profession. And with that spirit high, I wish everyone very happy computing journey. Wish you all a great success in your fields. Thank you everyone for joining.